on a current. So just like we learned, just like we discussed, the only thing that's different with a magnetic force on a current is that the charge, instead of moving freely in space, is moving along a wire in the form of a current. All right, so the magnetic field in the right-hand rule still points in the direction of the fingers. The current still points in the direction of the thumb, or the moving positive charge, and the palm tells me the direction of the magnetic force. Okay, so in this example here, it says the voice coil of a speaker has a diameter of 0.025 meters, contains 55 turns of wire, and is placed in a 0.10 Tesla magnetic field. The current in the voice coil is 2 amps. Okay, so here's essentially what we've got. We've got 55 turns of coil that of wire. Okay, we've got a magnetic field. Let me use a different color here. We've got a magnetic field that is going parallel to that, and this is essentially what happens in your speakers. Okay, so there's my magnetic field going through it. I want to know, I want to find out what the acceleration is on the coil. Okay, yes. So the first thing we would have to do is we would have to find the force. So we got this new equation. Okay, this is the equation for the force on a current. ILB sine theta as opposed to VB sine theta? QVB sine theta, right? In this case, it's ILB sine theta. All right. So with that equation, we would just plug in the force is equal to ILB sine theta. According to this problem, what's the current going through the coil? Okay, 2 amps. The length of the coil we're going to have to figure out. We know its diameter is 0.025, so I'm going to have to figure out the length. So I'm going to have to figure out the circumference from that. All right. So to figure out the circumference, I'm going to take the 0.025 and multiply that times pi. Is that right? So pi times 0.025 meters. Now that's for 1 turn. How many turns do I have? 55. So I have to multiply that times 55, because that's going to be the circumference of just one. So 55 of them is 55 times pi times the diameter. Okay, so that takes care of my length. That takes care of the length, that part right there. The magnetic field is how much? What is it? Oh, 0.1 Tesla. Okay, and we'll assume we're perpendicular to the field, so the sine of that's just going to be 1. Okay, so 0.10 Tesla. And then I get a value of 0.86 newtons, 0.86 newtons. Okay, so if I apply that current on that length of wire, how would I go about finding the acceleration then? Okay, yep, I definitely would need the mass. Okay, and in this particular problem, I didn't give you the mass. So let me give you the mass. The mass is 0.020 kilograms. Okay, so I would find that by using Newton's second law, taking the force and dividing it by the mass. So 0.86 newtons divided by 0.020 kilograms. And that turns out to be 43 meters per second squared. Okay? So that's the acceleration that a coil in the speaker would experience given that force and that mass. Okay? Yeah?
Is this what they use to find the field of electromagnetic?
When a current carrying loop is placed in a magnetic field, the loop tends to rotate such that its normal becomes aligned with the magnetic field. Okay, And the normal is this. So not only do currents experience forces from magnetic field, that's what we just proved, right? Currents on their own produce their own magnetic field around the wire. Okay, so if I've got a charge, let me use a different color here. If I've got, let me use red here. If I've got a charge in the form of a current going up in that direction, okay, a current on its own, based off the right-hand rule, produces a magnetic field that goes around the wire. All right, so based off the right-hand rule. So right-hand rule number 2 says grasp the wire and point the thumb in the direction of the current. The fingers will point in the direction of the magnetic field and will have that magnetic field strength. Okay, and it's based off how far you are from the current. So 1 over R is a relationship there. Okay? All right. So if we use our analogy here, okay, it says a current exerts a magnetic force on a moving charge. So a long straight wire carries a current of 3 amps. So let's just draw out a wire. Okay, and we'll say that there's 3 amps of current in it. A particle of charge 6.5 times 10 to the minus 6 coulombs is moving parallel to the wire at a distance r away from it. So here's my charge. It's moving with a velocity of 280 meters per second. And it's a distance r, 0.050 meters away. Okay? And we want to find the magnitude and direction of the magnetic force exerted on this moving charge. Okay? So the first thing we need to calculate out is the value of the magnetic field. So the magnetic field would have a value. Okay, so 1, 2. I'll make sure I have all of my parts here. Okay, so it says find the magnitude and direction of the magnetic force exerted along the moving charge. So first of all, I got to find the magnetic field. That'll be mu sub I, where mu is this value here, over 2 pi r. Okay, so I've got a magnetic field at this location right here. Okay, now that magnetic field that's at that location, are they going to be pointed into the page or out of the page? What rule are we going to use for that? Yeah, right-hand rule number 2. Okay, so we grab the wire. Okay, so we grab the wire, and above the wire, which way are my fingers pointing? Out towards us. So am I going to draw dots or X's? Dots. And that's what we talked about last time, Ty, that we use dots to represent coming out of the field. So we would have a magnetic field here that would point out at us. So just draw dots like that. Okay, so magnetic field is pointed that way, out at us. Okay, and then we've got to plug into our equation. We've got to plug this into our equation ILB or B, the QVB sine theta. QVB sine theta. Okay, so that's going to go into that part of the equation. So my force is going to be equal to the charge that is moving, its velocity. Now I got to plug in the magnetic field, and that I calculate by using this equation, mu sub 0 I over 2 pi r. So it's really important to know what to plug in. Times the sine of theta, and that'll just be the sine of 1. Okay, All right, so as I plug my values in here, what's the value of the charge for Q? Okay, good. 6.5 times 10 to the minus 6 coulombs. Okay. What's its velocity? Okay, 280 meters per second. Okay. Mu's value is that, you just have to put that in your calculator, 4 pi. 4 pi times 10 to the minus 7th. Okay. Times the current. What's the value of the current? Does it say? What's the value of the current?
3 amps.
Okay, 3 amps. And I divide that by 2 pi r. Okay. And how far is the charge from the current? How far? 0.05. Okay, 0.05 meters. And I get a value, I'll just tell you, of 2.2 times 10 to the minus 8 newtons. Okay? Now, what direction is that the object going to experience the force? Okay, we calculated out the force. That wasn't so hard. But which way is that force going, that object going to experience the force? Okay, good point. Towards the wire. So let's look at, let me use a different color here. Let me use like a dark green here. Okay, so it's going to experience a force in this direction. Okay, towards the wire. Because remember, our fingers point out at us, our thumb points in the direction of the moving charge, so my palm would point downward. Okay? All right, now, so now this is the kind of problem that I like to put on the test. Okay? It says 2 straight wires are separated by a distance of R is equal to 0.065 meters and carry currents of 15 amps and 7 amps. The magnitude and direction of the force that the magnetic field of wire 1 applies to a 1.5 meter length of wire 2 when the currents are in opposite directions. So we want to find the magnitude and direction when they're in opposite directions. Okay? So here's what's going to happen. I'm going to have a wire in this direction, okay, and we're going to point them in opposite directions. Okay, so for this wire on top, I'm going to say it's 15 amps, and this is 7 amps. Okay, you know, we won't actually, what I need to do is I need to find the magnetic field. So let's call this, this is I1. That's the current I1. This is the current I2. Okay. What will I1 do over to I2? What's it going to cause? What will it do? It's going to make a magnetic field down to I2, but in what direction? Okay, it's going to be into the paper. Okay? Because if I grab that top wire, my fingers down below will point into the page. So I'm going to have a magnetic field here that's into the paper, and this magnetic field, I'm going to call that B1.
You only need to find magnetic fields.
What's that?
You only need to find one of the magnetic fields.
Yeah, but we're going to look at how they affect each other. Okay, or the forces affect each other. Now, I2 is going to produce a magnetic field up in I1. What direction is I2's current going to produce the magnetic field?
Into the paper.
Into the paper. So I'm going to draw dots up here.
It should be X's.
Okay, so so X's. You're right. They're going to be X's because they're going to go.
On the inside or the outside of the
Okay. All through the region above and beneath it. Okay, so you're right. They're going to be X's, right? Because they're still going to be going into the page or into the paper. So these should actually be X's. Thank you for catching that. Okay. All right. So that would be B2. All right. Now, for I2, the current for I2, let's look at what direction they will be. Let's look at what direction it's going to experience a force. Okay. I2 is going to be forced in what direction? I2. It's got a current going to the left and a magnetic field going into the paper. So which way is it going to go? Okay, so as we grab it, okay, my fingers go into the page, my thumb goes that way. So my palm's pointing which way for I1? What's that?
Yeah, wait, what?
I tend to go bang.
Well, no, we're just looking at I1 right now.
You said I
Oh, okay. No, I meant the magnetic field from I2 onto I1. Okay, so let's look at what's happening to I1 from I2's magnetic field. Okay, so it's going to be pushed upward. All right, so it's going to experience a magnetic force upward like that. Okay, what about on the bottom wire? What about its force? Okay, so magnetic field goes into the paper, thumb goes to the left, so its force is going to be down like that. Okay, and we can calculate out all these forces. I just want to look at their values. Okay, so if we did, if they went in the same direction, okay, so we won't actually figure out the values. Let's just look at the direction because that's what's harder to figure out. So let's look at, let me change this ink color to the dark green here. So now let's say I1 and I2 are going in the same direction. So that's I1 and this is I2 going in that direction. Okay. Now I1, the magnetic field from I1, let me change the color here. The magnetic field on I1 down to I2 is going to be which way? No, the magnetic field coming from I1 down to I2 into the paper. Okay, so I still got X's there. Okay, and these would be from B1. Okay, what about the magnetic field on I1 from I2? Out of the paper, so I'm going to draw what there? I'm going to draw dots. Okay, and we'll label those B2. Okay, now what about the magnetic forces? Let's look at the magnetic forces. Now on I1, the force on I1 is going to point which way? Okay, it's going to point down because I got my fingers pointed out, my thumb in the direction of the current. So that's going to be forced down. So that's going to experience a force that way. Okay, and what about on I2? Yeah, my fingers go into the paper, my thumb goes to the right. So it's going to also experience a force, the value F. Okay, so this comes up on the multiple choice part of the AP test. The fact that when the currents go in opposite direction, the magnetic force between them repels. Okay, when the currents go in the same direction, they're going to attract. All right. Okay. So what I'm going to have you guys do is this.